Okay. Thank you very much. Is this good? Okay. I'm exceptionally pleased to be here and flattered to be invited to make a keynote presentation. This presentation, when I think about this, there's a movie that keeps coming to mind. In my case, The Matrix. I think I had a red pill, blue pill moment a few years ago, and I can't go back. And I think that's the same choice that I'm offering you today. Remember, all I'm offering you is the truth, nothing more. Now, currently, there's a debate between composite-based methods and primarily PLS. PLS is on the firing line, and factor-based methods. And a pretty good analogy is right here, only this is a little more civilized than the debate in the literature. And the worst part of it, I mean, I enjoy throwing mud like everyone else does, but it's not constructive. And I think it's distracting us from real issues that we are absolutely facing, that we need to solve so that we can move on and actually help people. And this is not helping people. And fundamentally, I think it distracts us from a crucial question, where we're putting a lot of effort into totally the wrong places. The main thesis for my talk is that arguments commonly used to support the notion that factor-based modeling is better than composite-based, better than PLS path modeling, are invalid. And we need to get past those and move on to a real discussion. Now, the particular arguments I want to talk about in brief, there's the latent variable argument that factor-based SEM involves latent variables and PLS doesn't. There's the bias argument, factor-based parameter estimates are unbiased, while PLS parameter estimates are not. There's the measurement error argument that says, well, factor modeling deals with measurement error, and PLS doesn't. And then there's the overall fit argument that says, well, factor-based modeling assesses overall fit, PLS doesn't. Every one of these arguments is invalid. I'm not saying false necessarily, but invalid as a basis for making a decision between factor-based SEM and composite-based approaches. Now, the first of these, factor modeling involves latent variables, while PLS does not. Well, when you say latent variable, what is a latent variable? And in the literature, from the very beginning, from the works of Charles Spearman, who invented both true score theory and factor modeling at the same time, about 111 years ago, there's two different meanings. One is the statistical meaning of a common factor. The other is the substantive meaning of a conceptual variable, the unseen, untouchable variables that drive behavior in the real world. Now, obviously, if latent variable means common factor, they've got us. PLS doesn't use common factors. And if they say, the problem is, I'm not Swedish, they've got me, because I'm not Swedish. But so what? Now, a quick review. I know I don't need to review much for this audience. So factor-based SEM, let's say we've got common factors, A, B, and C, and we've got observed variables, little a, 1, 2, 3, little b, little c, and we have a factor model where, let's say, factor C is dependent on factors A and B, and we have factor indicator models, so each, oh, bless me. So each indicator, say in the case of A, is dependent on the factor plus a residual or a specific factor, or as we too commonly say, an error term. And the same for B and C. Now, PLS, and With PLS, we routinely standardize our observed variables and our composites, and that's actually very important. It changes the mathematics of what we do just a little bit. But we have composites, A, B, and C, and we have observed variables, little a, little b, little c. We have an inner model. So here, composite C is dependent on composites A and B. And we have an outer model where A, for example, composite A, is a weighted sum of its indicators, and the same for B and C. The question being, how do we generate those weights? Now, the most familiar approaches are mode B and mode A, and mode B is a regression weight approach. We do a regression of the composite on the indicators together, and so we use those regression weights standardized. Mode A. In the PLS literature, historically, mode A is represented as something like factor analysis. And that something like, I think, is an argument that's held us back. What mode A really is, instead of using regression weights, we use correlation weights. So we do a regression of the composite on the observed variables, but we ignore collinearity amongst those observed variables. We ignore collinearity among the predictors. Now, why would you want to do that? We've all learned the regression story, you know, least squares regression is great, it has all these optimal properties, but you look at its out-of-sample prediction performance. A nice paper by Dana and Dawes from 2004 affirmed that correlation weights will beat regression weights in out-of-sample prediction under a wide range of conditions, under the practical conditions that we really encounter. And it was Theo Dijkstra who pointed me to this in his 2010 chapter in the PLS handbook. He made it just as clear as you can make it. And we've since confirmed this supposition, the idea, in simulations. Mode A, correlation weights. Mode B, regression weights. And of course, in principle, you could just take your indicators and sum them up. Use unit weights if you want to. But primarily, regression weights and correlation weights. But whichever, PLS, like generalized structured component analysis, GSCA, creates composites as weighted sums of their indicators. So factors, composites. Now, but back to that question. And the question was latent variables, the role of latent variables. Now, we go back again to Charles Spearman in 1904, and he gave us a model that looks something like this. We have a set of observed variables, and it's faint here, but each of those observed variables has its little halo of error. They're tainted by error, they're imperfect. And we have each of them being driven by a true score, which in the first half of the 20th century, true score meant something like long-run expected value. But it's changed since then. And this true score, Spearman derived through factor analysis. He invented both of them, true score theory and factor analysis, all in one go. I'm not surprised that the two continue to be connected. But something changed in the middle of the last century. Doesn't that make it sound like 1,000,000 years ago? In the middle of the last century. It's like I'm talking about, you know, some artists, you know, some style that vanished around 1950. Something changed, and that true score became not long-run expected value, but a conceptual variable, like need for cognition, or job satisfaction, or intention to leave, a variable that we can't touch or taste or smell, but that drives behavior. Not a statistical concept, but something in the real world, which nevertheless is just beyond our reach. Well, I want to suggest just a little further generalization, but I warn you, I've got two pills in my hand, a red pill and a blue pill, and you want to be careful. Now, in this world, we could talk about the quality of measures. We could assess reliability and validity based on the gap between our observed variables and this true score, this thing that we're used to extracting via factor analysis. But I want to suggest to you a different world. Suppose, just suppose, that the factor that we extract is not identical to the conceptual variable in our substantive model. Suppose it's only a proxy, an approximation. Maybe it's a great approximation, and we can just assume, we can just plant an equality between the proxy and the conceptual variable itself. Or maybe we shouldn't do that at all, ever, because it's unwise. It ignores reality to assume that that common factor and that conceptual variable are identical. If you will go that far with me, that they might be different, well then, we could use factor analysis here, but we don't have to. We could consider something else. A wide range of mathematical operations, including weighted sums. If we use weighted sums to create a proxy for our conceptual variable, well, that's PLS. PLS and generalized structure component analysis, and just summing things up. A lot of variations and more that we haven't even talked about. Or we could use factor analysis. Either way, we're creating a proxy to represent a conceptual variable. And our question should be, how good is that proxy? Is it doing a good job of representing the conceptual variable or a poor job? Imagine if it's doing a poor job. We have a proxy there that we're calling job satisfaction. But what if it doesn't really reflect job satisfaction very well? Well, then our conclusions are completely invalid. We haven't learned anything from our research. Watch out. I think I see some of you reaching for the red pill. Be careful. So the argument was, factor analysis, factor-based SEM involves latent variables, and PLS does not. I disagree strongly. Without that conceptual variable, which is our latent variable, it is driving behavior, and it is beyond our reach, outside the statistical model. Without that conceptual variable, it's not clear what we're accomplishing, what we're doing with our modeling. Without that conceptual variable, maybe all we're doing is just data description. We need those conceptual variables to give meaning to our work, whether we're using factor analysis or PLS or anything else. So as far as argument one goes, I say factor analysis and PLS are on precisely the same footing. If there's a difference, it's that the PLS community is maybe a little more ready to recognize the distinction between conceptual variable and proxy or representation than the factor community may be ready for. Second argument, bias. Now, PLS estimates biased. Well, you go back to Hermann Vold, and he wrote that PLS was an intentional approximation, right? We all know this. Back in the days when computer resources were scarce, you had to go to the computer center, take your box of cards. I just remember that. I just had time to enjoy that before the world moved on. And you didn't want to waste a run, a chance at the mainframe. So an intentional approximation kind of implies that the estimates were not the best. They're maybe biased. He wrote they were biased. Moreover, in recent literature, Aguirre, Rita, and Maracas, Ronco, and Everman, of course, have criticized the quality of PLS estimates, and there's more. And there's more in that literature. And Thiel and Jorg's consistent PLS. Well, if you have to adjust it to make it consistent, that implies that without the adjustment, it's biased. We all know there's a bias this way and a bias that way. My counter-argument here is PLS estimates aren't biased because PLS is defective. They're biased in the literature because people insist on thinking in terms of a factor-based world. They draw their simulation data from factor-based populations. And for a factor-based population, yes, PLS model is misspecified. But in a composite-based world, drawing data from composite-based populations, PLS is not misspecified. And if you did that, then you should expect your parameter estimates to be at least consistent, if not unbiased. And in 2013, in a paper at ISIS, the International Commission Conference on Information Systems, there we go. We published a paper which illustrated some of, I say our simulations, I should say Jan Michael's simulations. He kindly put our names on the paper. Jan Michael's simulations, which showed precisely that. If you build composite-based populations and use PLS to estimate parameters, there isn't bias. The estimates are consistent. So it's not a failure of PLS, it was a misspecification of the model. Now, how did we do this? We all know how to generate factor model data. I mean, we can do it, right? You can do it in your head. You can almost generate data just coughing up the numbers. Now, here was the model that we used, and it's a very simple model. We have two composites, x1, x2, predicting another composite y. Each one has 4 indicators, and we formed the composites, weighted sums. And one thing we wanted to manipulate was the R² for the dependent composite, because Dana and Dawes showed that the performance of regression weights varies depending on the true R², the true predictability of the dependent variable. So he did it this way. I'm going to keep saying we now and then, but you understand when I say we, I mean pretty much Jan Michael. We, there I did it again, did it by leaving P1 fixed at a small number, 0.3, and then, varied the level of P2 up or down to produce the R² that we wanted overall. Now, how do we generate composite-based populations? It's easiest to understand that if you think of sigma, the covariance matrix of the observed variables, the x's and the y's, as a partitioned matrix. So we have sigma xx down here, sigma xx down here, which is the covariance matrix of the on the x side, and sigma yy is the covariance matrix on the y side. And then we have the cross covariances, the covariances of the x's and the y's. Take it in pieces, and it's so simple. It's like, why didn't we do this 20 years ago? Now, if this was a factor model, then the covariances, the sigma yy, sigma xx, covariances would all be driven by the loadings of the indicators on the common factor. But this is a composite model, so we have to specify. We have to specify how the components covary. We also have to specify the weights, how the components come together to form the composite. That's up to us. And we have to specify the paths, the strength of P1 and P2. And once we've specified all of those things, the last thing to do is to calculate the cross covariances, the covariances of the x's with the y's. And we do that using path tracing rules. The covariance xy is equal to the covariances of the y's times the weights, times the path coefficients, times the other set of weights, times the covariances on the x side. And that gives you sigma xy. And bang, you've specified a composite-based population. And when you do that, you get results that look like this. This is just a sample of those results. There's another manuscript in preparation. I'm hoping that it's farther in preparation very soon. Now, things we varied. We varied sample size, 40, 100, and 500. We've done some additional simulations with even larger samples. And here are the results for the coefficients P1 and P2. And what we're presenting here is mean bias. And remember, we varied R squared in the populations. What's the true predictability of the dependent composite? And the solid line represents the bias in mode B regression weights. The dotted line, or dashed line, bias in the mode A correlation weights. Now here's the zero line. If we were right on the zero line, that would mean there was no mean bias. And down here, the tiny dotted line is unit weights. What if we just summed up the standardized standardized indicators and used them? Well, if you use unit weights, well, you have a negative bias. You're underestimating P1, and that doesn't change because the value of P1 doesn't change. There's no reason it should change at all. But you see what's happening, that mode B and mode A, the mean bias is positive when R squared is low, 0.2, but it becomes negative, it crosses the zero line, when R squared is high at 0.8. So at a sample size of 40, the bias is positive at low R squared, negative at high R squared. Now down here for P2, remember P2 varies. As R squared goes up, P2 itself rises, its true value rises. But we still have the same pattern of positive bias at low R squared, negative bias at high R squared. But now here, see, the unit weights do worse and worse as R squared goes up, because P2 is getting larger and larger itself. There's more room for bias. But as we increase sample size, you see this line, which is relatively steep here, becomes flatter, and it gets closer at more places to the zero line. And when we go to 500, you see both mode B and mode A are very close to that zero line. We increase sample size further, and even more of the gap disappears, both for P1 and for P2. And this is the general result that we found. When the population is correctly specified, PLS estimates unbiased? I wouldn't say so, but consistent. PLS estimates are consistent when the population is correctly specified. It's not a PLS problem, it's a model misspecification problem. And if we gave our data to a factor method and said, come on, estimate our model, not even close. So maybe factor methods have this inherent problem. You know, maybe we should just stop using those because they're defective. No. We should figure out, what the real problem is and deal with that. Now, if your sample size is small, and I know PLS history, small sample sizes. If your sample size is small, or your model's not identified, well, you're going to have problems. You're going to have bias. You can't pretend otherwise. Not only are your parameter estimates going to be biased, but your out-of-sample prediction is going to be weak. But the same is true for factor analysis. If a factor model, you have your sample size is too low, or you violate the identification rules for a factor model, your parameter estimates are not going to be very good at all. That's just basic. I mean, that's for any method. There are identification constraints, there are sample size requirements. Argument number 3, and I'm not keeping time, so good luck to you all. Factor-based SEM accounts for measurement error. Oh yeah, that's a big one. And PLS, of course, doesn't. We'll jump to the PLS part. If PLS uses weighted sums of indicators that are themselves tainted with error, well, the weighted sum is going to be tainted with error. I know in the formative measurement literature, there are people say, well, if it's formative measures, you assume no error. Come on. A minute ago, it had error. Now you're using it in a formative model, you're going to tell me it has no error. Of course it has error. And some of it's going to make its way into that weighted composite. Not as much, but some. Now, factor-based SEM does separate common factor from that E term, which you could call a specific factor, which you could call a residual, but which has been called measurement error. It's been labeled measurement error. And in Boland's '89 factor-based SEM book, which in 1989, today, still the best book on factor-based SEM ever written, which is really kind of unfortunate because it's 25 years old. Come on, people. Come on. Move forward. I want something better. Good luck. Explicitly linked the common factor to the true score, which meant that the residual was therefore measurement error. And again, we know that PLS using composites, if the components have error, the composite will have some error in it. It will. So let's take another look. Yeah. I agree with Lee Cronbach and colleagues when they wrote, tidy theory of error laid down for psychology at the start of the century by Spearman and William Brown. And they mean the last century, not this one. Has always seemed just a little too tidy to describe the perverse behavior of real data. Does anyone not agree with this sentiment? Data misbehave, and not in simple ways that we can easily counter. Now, my counter-argument here is that while PLS, 10 minutes? Thank you. While PLS weighted composites are tainted with error, common factors are also tainted with error, also through the phenomenon of factor indeterminacy. Now, briefly, here's a basic factor model where our dependent y's are dependent on common factors and specific factors z, and we assume that the common factors and specific factors are orthogonal to each other, so we get the covariant structure sigma, the covariances of the y's, lambda times phi times lambda transpose plus theta. And I want to consolidate phi and theta. I can do that easily because I know they're orthogonal. I assumed that the common factors and specific factors are orthogonal. So I can put them all into one matrix psi, and it looks like this. But here's the thing. I took my data, if I've got p observed variables, then the rank of the covariance matrix of the data was p, at most p, assuming nothing is redundant. So I've got p dimensions of information, as Stan Malik says. But on the other side, in my factor model, the rank of this psi is now p plus k. If there are k factors, the rank is now p plus k. I turn p things into p plus k things, which if I could do that with euros, you know, I wouldn't be wasting my time here. I'd be off being rich somewhere. How do we do that? How do we do that little miracle? Well, we do it by making the common and specific factors indeterminate. Now we can represent the common factors as a function of model parameters plus times the covariance matrix of the indicators times the data plus P times S. Plus P times S. Now S is an arbitrary vector. Not random, but arbitrary. Within certain limits, it can be anything. But it must be there. So what's P? Well, P times P transpose. Let's simplify that. Let's make this one common factor. Then this is a single number, and the square of that number is a function of model parameters. Let's say it's one factor and it's standardized, so it has a variance of 1. So P squared equals 1 minus something. What's that something? Well, it turns out that something is R squared. It's the R squared that we get if we predict the common factor using all of the observed variables in the model. And that R squared is approximately McDonald's coefficient omega, or what we call composite reliability. So when our measures are weak and our reliability is low, P is high. This is 1 minus R squared. This is a reflection of measurement error. The weaker our measures, the larger the arbitrary component in the factor, the more error it contains. Factor-based SEM does not eliminate measurement error, just as PLS does not eliminate measurement error. Neither approach does that except at the limit. To expand my model just a little bit, here's where we stood, but I say, oh, you can't even make it out. Our proxy has a haze of error of its own. It's not error-free. For whichever method we use, there's error there, just a question of how much. I argue further that where we should be measuring, assessing reliability and validity is not between the indicators and the proxy. The question is, how good is the proxy as a representation of the conceptual variable? That's error right there. That's where we should be assessing reliability and validity. How far is the proxy from the conceptual variable it represents? And we're not doing that. How much error? That would tell us what's our reliability. How far proxy from the conceptual variable? That's validity. Now, the factor community ignores indeterminacy. They love to ignore factor indeterminacy because it does not affect, it does not bias parameters within the factor model. It does not. Guaranteed, it doesn't. But it does blur relations between factors within the model and any variable outside the model. Blur, because S, the arbitrary component, can be random or systematic. It could be correlated with something outside the model. It could have a positive correlation or a negative correlation with any particular something outside the model. Factor modelers tend to say, I don't care about outside the model. I care about inside the model. But you should care, because the conceptual variable is outside the model. Therefore, factor indeterminacy blurs the relationship between the factor as proxy and the conceptual variable that it represents. So again, factor-based SEM, composite-based SEM, does measurement error go away? No, it doesn't. It's still there. We need to deal with it either way. The fourth argument, factor-based SEM assesses overall fit and PLS does not. Yes, there's a chi-square. Absolutely there is. But does it matter? Does the chi-square make a difference? No. in factor analytic terms, here's our model. We use factor analysis, create a proxy, there's a conceptual variable, we get a chi-square. And let's say the chi-square fit is bad. Awful. Ooh. Like, any typical model that we estimate. It's pretty bad. Carl Jureskog, back in 1969, did the best job of explaining what that bad chi-square means. What it means is, well, if the value of chi-square is obtained that's high relative to the degrees of freedom, that's an indication that more information can be extracted from the data. Okay, there's more. That's great. My wife raises goats and makes cheese. She milks them and makes cheese. You make cheese, there's a runoff whey, a liquid, which you can use for a lot of things. There's something in the whey that's valuable. Doesn't mean it's bad cheese just because there was runoff. The question is, so in itself, I don't think a bad chi-square tells you that the proxy itself is good or bad. Okay, there's more information in the data. So there's more information in the data, but the question is that proxy a good representation of that conceptual variable? By focusing on the chi-square, we're missing the point. But let's say your fit is great. You have a really good fit. You're dreaming, right? You're asleep and you're pretending, and you have many indicators, and your model fits very well. Yeah, so let's say like this factor F. Our model fits well. Maybe that factor F is a good proxy for A, but not such a good proxy for B. B is farther away. But A and B are not in the statistical model. So if we have a good chi-square thinking that F proxies for A, we have the same chi-square with F proxying for B. The good chi-square doesn't tell us that F is a good proxy. It just says there's nothing left in the data to explain. I don't see how overall fit assessment tells us that factors make better proxies, even when the model fits well. I don't think there's any argument. And I happened to see Carl last month, and I'm pretty confident he'd agree with you, or agree with me. He might agree with you too. So I don't think any of these arguments is a valid basis for distinguishing between factor-based proxies and composite proxies to say that factor analysis is a better approach than PLS path modeling. Well, what would be a valid basis for distinguishing a better proxy from a worse one? I know I've only got so many minutes left. Give me the sign. Well, I think this is self-explanatory. Oh, come on, I got a laugh in Connecticut when I said that. Let's say the truth, the conceptual model, involves conceptual variables A, B, C, and D in this relationship. And let's say we know the value of, say, V1. We know V1, and we know V4. And we create a set of proxies to represent these conceptual variables. And we have estimates of V1, V2, V3, and V4. How would we assess the quality of our proxies? Well, we could compare that V1 to that one. If these A and B star, A star and B star are good proxies, this V1 should be that V1. And if we know this V4, then these two proxies should reproduce that V4, or we might go further and fix the values that we know to the values that we know are correct. Fix the values and live with those constraints. Now, we don't do that. PLS, we don't do that. Factor analysis, we don't do that. Every time we estimate a model, we estimate the parameters all over again. Like we don't know anything. Like it's the very first study. After 50 years of applied SEM, it's 51st dates. we do it all over again from the very first time. And I think that's nuts. We should be learning something and using that knowledge to make our methods more powerful and more rigorous and move ourselves forward. Now, rejecting these arguments, these 4 arguments, doesn't mean that PLS is in the clear. All right, now we can just do whatever we want. To be useful for studying conceptual variables, we must either enable meaningful assessment of the proxies that we use, composites or factors, or else we need to sharply constrain our conclusions. To not say, I'm telling you something about job satisfaction, just I'm telling you something about a weighted sum of these observed variables. Because I don't have a valid basis to say that that stands for job satisfaction. To have good proxies, almost certainly we're going to need large sample sizes. You see the performance of PLS parameter estimates at very small sample sizes. We can't expect our out-of-sample R-squared to be very high. We can't expect to be reproducing parameter estimates accurately. We've got to deal with the qualities of our measures. If our measures are, say, ordinal, we've got to address that. We can't just pretend that they're continuous when we know they're not. We've got to take full advantage of prior information. If we know something about parameter estimates, we've got to use that knowledge. And if we don't know anything about parameter estimates after decades of research, I think we've got to ask a different question of why haven't we learned anything after 40 or 50 years? Feynman, Robert Feynman, the physicist, described what he called the scientific imagination. He didn't mean the ability to invent things that aren't there. He meant the ability to recognize what's plainly in front of us. He said that a new explanation had to meet this condition, that it had to deal with the facts that we had. It had to be constrained to fit those known facts, like a straitjacket. I think we need more of that in our fields. Use the information we collect, keep it, and make our new explanations conform to it. We have to think more about exploratory applications. If exploratory means, well, I have a bunch of observed variables, I really don't know what conceptual variables might be, I don't know how they behave, I'm really not in a position to tell you whether my proxy is good or bad, then we have to be careful in making conclusions about conceptual variables when we're saying explicitly, I cannot evaluate my proxies. Thank you very much. And if you have any questions, I'd be happy to have them.
Yeah, thank you very much, Ed. And we have some time left for questions, about 5 minutes. There's also a possibility tomorrow, in the last session, we will have a panel discussion, where also a possibility for questions will still be given. However, feel free to ask questions. Questions that immediately follow up. Yes. Thank you very much.
Thank you very much. Dr. Shaltuni, Al Faisal University. I'm just interested in your thoughts. Do you think that this war will end between the factor-based and the composite-based, or shall I say it, the war or the game? What do you think? I mean, because we all keep thinking, when will this end, if there is an end for that?
Well, I think that there are a lot of good people on both sides, and strong arguments eventually win. There's the geologist, von Humboldt, who talked about the 3 stages of scientific progress. Where in the first stage, they say it's not true, and in the second stage, they say it's not important, and in the third stage, they give the credit to the wrong person. So I think we're moving well into stage 2, and I'm looking forward to find out who gets the credit when we get to stage 3. But I think we're going to get there. I mean, if we're scientists, if enough of us are scientists, then inevitably, I think we find our way closer to the truth.
More questions?
Theo Dijkstra. Thank you, Ed, for your nice presentation. It reminded me of the hope that Christian Ringler expressed this morning, that practitioners would not go home confused. I can guarantee you they will, because at the end of the day, I will give my keynote talk, and if they are not confused, I don't know what we did today. One thing I would like to ask you very concretely is, how do you assess the quality of the proxy?
Now, first of all, my thinking doesn't get anywhere close to where it is now without Theo's contributions. He opened doors, turned on lights for me.
That's not why I asked the question. But thank you anyway.
I think we cannot assess the quality of our proxies unless we know something about these conceptual variables. You go back to earlier writers on validity issues. There was a fellow in management named, was it Schwab or Schwann? I don't remember. Anyway, in order to learn something, you have to know something. If you don't know anything, then no, we're dead in the water. We have no shot. But if you know a little something, some piece of how these conceptual variables behave, then that's your criterion. Can you reproduce that thing that you know? And that's where, if we were physicists, that's where we would start. Gravitational constant. We know what that sucker is, so we can reason about other aspects of a physical model from that one thing. I'm afraid in the social sciences, we're far away from that. That won't surprise anybody. We're far away from that. Again, we seem to reinvent the world every time we do a study. Another line from the same movie. I didn't say it would be easy. I only said it would be the truth. It's definitely not easy, whether it's the truth or not. Yeah.
Good. I think these were also some great words to terminate this session. Before we go to the coffee break, I would like to ask you for a favor. We'd like to make a photo of all of you, of the whole group of participants. So I'd kind of like to ask you to come in front, so we can use the stairs here, so that the photographers can take a photo of all of us. Thank you, and then within 2-3 minutes, we'll have a coffee break at the Salon de Grados, which is where the registration took place. Thank you.